It is Tuesday, March 17th. So happy St. Patrick's Day out there for everyone. I kind of wish we were in the building today because I'm always interested to see which students wear green and which students also wear something really kind of creative or silly just for the day. Right? You don't have to actually be Irish to wear something silly or green on St. Patrick's Day. We're going to be taking a look at logarithms. We've actually worked with part of this skill before. Way back first semester, we worked with some powers and roots, and I'll be referencing that in a few slides. And since this is a video, you can always pause at any point if I start going too fast, or if you want to pause it and try to work something on your own before I reveal an answer. You can rewind it, watch it again. If you would rather just download the PowerPoint without my narration, that is available on Quick Schools. You can do it both with animation, or if you really just want the slides with the definitions and examples, download the one that says low animation. Right? The regular one is going to have everything that you see here, with the exception of my narration. But if you do the one with low animation, you will really just get the notes, the definitions, the examples. Okay, now let's head way back to elementary school for just a moment, and remember some number families. Like if I gave you 4, 6, and 24. You learn that not only could you write them as a multiplication fact, 4 times 6 is 24, you could also write them as a division fact. 24 divided by 6 equals 4. If I gave you 3, 5, and 8, you say, hey, I can write it as an addition fact. I can write it as a subtraction fact. Well, same thing with exponential functions. Now, if you remember from previous lessons, we were working with exponential functions. We spent one day where we actually plotted y equals 2 to the x power by hand, where we plugged in the values for x, and we learned what these functions look like when we graph them. And same number family can be written the opposite direction. So instead of writing it as an exponential function, I can also write it as a logarithm. All right. So b is going to be the base. The base has to be a positive number, and the base will not be 1. Problem with the base of 1, 1 raised to any power is still 1, so that's not really a function. That's a constant, right? 1 to the second power is 1. 1 to the third power is 1. 1 to the fourth power is 1. Doesn't do us any good to have a base of 1. Right? So the logarithm of y with base b is denoted by log base b of y, and it's defined as log base b of y equals x. Now, the interesting thing about this is that the b, of course, is the base. The x is the exponent. Right? So if we write it as an exponential function, we're looking at y equals b to the x, or as it's written this way, b to the x power equals y. Right? B is the base. There'll be a positive number, and it won't be 1. And so y also has to be a positive number, because if the base is positive, no matter what exponent I put up there, I'm going to get a positive answer. For example, 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. Right? If the base is positive, after I raise it to an exponent, my value will be positive. And so that expression is read log base b of y. So if we talk about logarithmic form, or if we talk about exponential form, those are the two different formats we want. So just like with a number family, we might have said, hey, give us a multiplication fact and a division fact. Or we might have said, hey, can you give us an addition fact and a subtraction fact? Here we can go both directions. I can either say, hey, if I give you the exponential form, can you give me a logarithmic form? Or if I give you the logarithmic form, can you give me the exponential form? Now, for some of us, this makes perfect sense because we can read the definitions and understand. For some of us, this is just gobbledygook, and we're like, hey, can you please show me some examples with numbers so I can understand what you're talking about? So sure enough, let's take a look at a few examples. And at first, we're just going to try practice rewriting these. So here it is in logarithmic form. Log base 2 of 8 equals 3. I want to rewrite that in exponential form. Well, the base is 2. The exponent is 3. So I need 2 to the third power equals 8. And of course, that's a true statement. 2 times 2 times 2 does equal 8. What if I've got log base 5 of 25 equals 2? Remember, you can always pause the video if you want to try to figure it out before I reveal an answer. Well, the base is 5, the exponent is 2, and sure enough, 5 to the second power is equal to 25. Log base 7 of 7 equals 1. Okay, so the base is 7, the exponent is 1, and sure enough, 7 to the first power does equal 7. Log base 3 of 1 equals 0. Okay, I can identify the base, which has to be 3. I can identify the exponent, which is 0. And 3 to the 0 power equals 1. Right? Any number raised to the power of 0 equals 1. I should note that the base cannot be 0 because 0 to the 0 power is undefined. But any number besides 0 raised to the 0 power is 1. Hey, let's go the opposite direction. If I give you the exponential form, I want you to rewrite it in the logarithmic form. 4 squared equals 16. Well, the base is 4, and the exponent is 2. So the 2 will be all by itself off to the right-hand side. I'll have log base 4 of 16 equals 2. Right? The base gets to be written as a subscript with the log, so the base was 4, right, because it was 4 squared, so it's log base 4. The exponent of 2, that's going to be all by itself over there on the right-hand side, equals 2. Log base 4 of 16 equals 2. When you're looking at a logarithm, you're actually just looking at an exponent. So if you hear about an earthquake with magnitude 7.3, that means that the exponent was 7.3, right? The amount of energy released was 10 raised to the 7.3 power. Same thing with, probably don't use these anymore, but old-fashioned cameras where you put film in them and you focused and you had to set an f-stop. Those settings were logarithms. If I can think of another day-to-day example of logarithm, I will, but at the moment, I think magnitudes of earthquakes would be the one that you're most familiar with. 8 to the 0 power equals 1. Okay, so the base is 8, so I need log base 8. The exponent is 0, so that's going to be the number all by itself. Log base 8 of 1 equals 0, because 8 raised to the 0 power has a value of 1. Again, notice the base is always positive, and the value that we end up with is always positive. So far I've been spoiling you because I've been making all the exponents positive, but we'll find out that that doesn't have to be the case, right? The exponents are allowed to be negative. So here's a cool example. 6 to the first power equals 1. So the base is 6. I need log base 6. The value looks like 6. I need log base 6 of 6. Exponent is 1. Log base 6 of 6 equals 1. Looks like there's room for one more example. 2 to the fifth power equals 32. Okay, base looks like it is a 2, right? It's 2 to the fifth power, so the base is 2. So it's log base 2. We ended up with a value of 32, so log base 2 of 32. Exponent is 5, so that has to be off by itself. Log base 2 of 32 equals 5. Now, as much fun as it is just rewriting them, I love solving equations. Oh yeah, let's solve this equation. Log base 3 of 81 equals x. Now you're probably thinking, hey, you just started teaching us logarithms, and this is really brand new, and I'm not even too sure I fully understand what that means. Well, let's rewrite it. You know the base is 3. You know the exponent has to be x. So I can rewrite that equation as 3 to the x power equals 81. That makes a lot more sense to me. I'm used to seeing equations that look like that. Now, one possible way about this is guess and check. Right? 81 is 9 times 9. But I need a base of 3. Hey, each of those 9s can be 3 times 3. Right? 3 times 3 makes the first 9. 3 times 3 makes the second 9. So 3 times 3 times 3 times 3 makes 81. Right? 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So it looks like I've got 4 of those 3's being multiplied together. So that must be 3 to the fourth power. 3 to the fourth power is going to be 81. X has to be 4. Right? When I see it written in logarithmic form, it doesn't make any common sense for me. I rewrite it exponentially, and then I can start to explore the equation. Log base 2 of 1/8 equals x. Again, I'm thinking, hey, this doesn't make any sense to me written as a logarithm. Fine. You know the base has to be 2. You know the exponent has to be x. 2 raised to the x power has to be 1/8. 2 to the x power has to be 1/8. Well, I know 8 is 2 times 4. Hey, that 4 can be rewritten as 2 times 2. So it looks like I've got 1/2 times 2 times 2. In other words, 1/2 to the third power. But because the 2 times 2 times 2 is in the denominator, I don't really have 2 to the third power. I have 2 to the -3 power, right? 2 to the third power would tell me I'm multiplying 3 2's together. But if it's a -3 for an exponent, instead of multiplying by the number 2, I'm dividing by the number 2. So 2 to the -3rd power would be 1 divided by 2, divided by 2, divided by 2. Right? 1 divided by 2 is a half. A half divided by 2 is a fourth. A fourth divided by 2 is an eighth. X has to be -3. Right? If I put the 2 in the denominator and cube it, I'll get 1/8. So there's our first example where we have a negative exponent. The base is still positive, right? The base is a +2. The base will always be positive. The value when we're done is 1/8. That's a positive number, but it is possible for the exponent to be negative. Log base 49 of 7 equals x. Again, if it doesn't make any sense to me written this way, I can rewrite it. The base is 49. The exponent is x. The value has to be 7. Well, I know 7 is the square root of 49. And I know square root is really an exponent of 1/2. So 49 to the 1/2 power is the same thing as square root of 49. The exponent has to be 1/2. Okay, so it looks like we're still solving equations. Ooh, the x is in a different location. This should be fun. Now we're looking for the base. X to the 3rd power has to be 64. Well, I know 64 is 8 times 8. But that's only 2 equal factors, right? 8 times 8 makes 64, but that'd be 8 squared. So I can't consider that. Now 64 is also 2 times 2 times 2 times 2 times 2 times 2. If you do much with computer programming, you're probably pretty familiar with base 2, right? Binary functions. That's not going to work because, well, that's 6 equal factors. I need 3 equal factors, so that's not going to do. Hey, how about 4 times 4 times 4? That would be 3 equal factors that multiply together to make 64. So if x to the 3rd equals 64, I must be talking about 4 to the 3rd power is 64, so x is 4. Now, first slide, I alluded to Unit 4 that we did in first semester. And you might remember from Unit 4 in first semester, I gave you an exponential table where you've got the bases in the left-hand column and the exponents in the top row. So, if I know that my exponent is a 3 and I want a value of 64, I can use the table and see that the base is 4, right? 4 to the 3rd power is 64. If you still have your copy of this table, fantastic. If you do not have a copy of this table, I have one available for download on Quick Schools. And you can either just open it and look at it, or if you want to download it and print a copy, download it and print a copy. Okay, let's get back to our examples. Log base 9 of x equals 2. Now again, when I'm looking at this, that logarithm, it doesn't mean much to me, right? I'm scratching my head along with everybody else. I'm like, okay, the base is 9, the exponent is 2. So I'm going to rewrite it as this equation, 9 squared equals x, right? Base is 9, exponent is 2. Well, 9 squared means 9 times 9. And 9 times 9 is 81. So sure enough, x has to be 81. I apologize if there's some background noise. I've got a dog that is chewing on a nylabone at the moment. He's not very quiet. Log base 8 1/4 equals x. Okay, so the base is 8, the exponent is x, and 8 to the x power has to have a value of 1/4. How on earth do I make an 8 turn into a 4? Now remember, we've got our exponential table. And I'm looking at an 8 and I'm looking at a 4. Okay, if my values are 8 and 4, it looks like they have a common base of 2. And it looks like the exponents I need to play with are 2 and 3. So if I start with 8 and I want to shrink it down to a 4, my exponent would be 2/3. 8 to the 2/3 power makes 4. Oh, but look at that. It's not 4. I want 1/4. Right? If I just wanted 4, that'd be a piece of cake. 8 to the 2/3 power is 4. But I need the 4 in the denominator of a fraction. So I need an exponent of -2/3. Right? If I take the cube root of 8, that would bring me all the way down to a 2. If I square it, that'll push me back up to a 4. And then, of course, the negative on the exponent tells me to do the reciprocal. So x is -2/3. Besides this PowerPoint on Quick Schools, I've also have available the PowerPoint from Unit 4, Lesson 1, which is where we learned how to work with the powers and the roots. It does not have my narration, but it is the PowerPoint we looked at in class. And so if you really want to refresh your memory, one good possibility would be to say, hey, let me relive that PowerPoint from Unit 4, Lesson number 1, when we were introduced to powers and roots. And again, if you want to look at all those examples at once, there they are on one screen. And if you download the PowerPoint with the low animation, you'll be able to just see a screen like that, so you can see what the answers are with the examples. Now, there are two bases that get used more than any other. The one, it's probably something you can guess quite quickly, base 10, right? When we talk about magnitudes of earthquakes, we're talking about the exponent, but the base is always 10. So a 7.1 magnitude earthquake is 10 to the 7.1 power. Or on those good old-fashioned cameras where you did your manual adjustments, maybe you put a 400 speed film in instead of a 100 speed film, because you use 100 speed film if you're just taking a picture of a mountain in the distance. But if you're a track meet and you got athletes running around, you might want a 400 speed film instead. Again, those f-stops on an SLR 35mm camera would have just basically been exponents, right? They would have been logarithms of 10 to some power. So if the exponential form looks like this, 10 to the third power equals 1,000, let's rewrite it in logarithmic form. You ready for this? Log 1,000 equals 3. Now maybe you're thinking I made a typo. You're like, hey, shouldn't it be log base 10 of a 1,000 equals 3? Well, here come those lazy mathematicians. Right? We love to show step-by-step work, but there's one silly thing we tend to do. Right? When we're looking at roots, and we did this a few units ago, right? Notice with the square root, we never put the little 2 in there, right? Fifth root, we use that little 5. Fourth root, we use that little indus of 4. Cube root, again, we've got the 3 there where the indus belongs. Square root, technically the indus should be 2, right? There should be a little tiny 2 in there, but we don't show it. Same thing with logarithms. Log base 6, log base 3, log base 27. But if it's base 10, we just write log. So just like with square root, mathematicians are so lazy, we won't put that little tiny 2 where it belongs. Same thing with logarithms. If it's base 10, we get so lazy, we don't put the 10. So if you just see log, if you just see log, you go, oh, that's log base 10, also known as a common logarithm. Oh, wait a minute here. Top of the page, it says we're going to look at 2 bases that are used most often. That's only one of the bases, right? Base 10 is one of the special ones. What's the other special base? So what other number gets its own special notation? If you were paying attention in class, previous lesson, you probably have a good guess about this. Remember, we use base 10 because we learned to count on our 10 fingers. Most societies in the history of this planet used base 10. A few use base 20 because they've got 10 fingers and 10 toes. And then a few civilizations use some really bizarre bases, but most, the vast majority of all civilizations and all cultures on this planet use base 10 because we counted on our fingers. Who's got a different number of fingers? That's right. If you remember Mother Nature has E fingers. Remember E? 2.718281828459045 ... So base 10 is known as the common logarithm, and we just put log. Base E is also known as the natural logarithm, because that is the base that occurs in nature. It occurs naturally. So instead of log base E, we'll put log as ln, right? We don't even write out the whole word log. ln. The L lets you know it's a logarithm. The N lets you know it's the natural log. It's base E. So instead of log base 10, we just write log. Instead of log base E, we write ln. How common are these? How frequently are they used? Take a look at your scientific calculator. Now, if you don't have a more modern, recent calculator, you might have to go onto your catalog menu. But if you have like a TI-83 or a TI-84, you'll notice that there's a button for log and a button for natural log. And if you look at the secondary function on log, it's 10 raised to the x power, right? The base is 10. If you look at the secondary feature on the natural log button, it's e to the x, right? The base is e, right? We use these so often in mathematics that, surprise, surprise, they're right there on scientific calculators. Now again, if you've got an older model, you might have to go through your catalog to find it. But if you've got a more up-to-date calculator, you should be able to find a button for log and a button for natural log. Or sometimes one button will toggle back and forth between log and natural log, and the other button will toggle back and forth between 10 to the x power and e to the x power. But they should be grouped right next to each other, right, either left and right of each other or above and below each other. So let's revisit a skill that we did early on in this lesson. Rewrite it in exponential form. So again, I need to figure out the base. I need to figure out the exponent, and I'll set that equal to my value. Well, I don't see a base, so I know it's going to be 10. The exponent, of course, is 3. So the 10 raised to the third power has a value of 1,000. That's true. You can double check that. 10 times 10 times 10 makes 1,000. ln of 54.598 is approximately equal to 4. Here comes the problem with base e. Because e is a transcendental number, we're not going to get very nice numbers out of this. Right? Either the exponent is going to have to be a really weird number, or the value is going to have to be a really weird number, or sometimes even both. So again, if I see ln, logarithm natural, or natural log, that's really log base e. The base is e, the exponent is 4, and e to the fourth power is approximately equal to 54.598 ... Right? Because e is between 2 and 3. So 2 to the fourth power would only be 16. That's too small. 3 to the fourth power would be 81. That's too big. So I know e to the fourth has to be somewhere between 16 and 81. But that's a really super rough estimate. So that's, thank goodness they've got calculators for if I want to get an approximate value. Natural log of 1 over e equals -1. Now again, the base is e. If I see natural log, the base is e. The exponent has to be -1. So e to the -1 power equals 1 over e. Right? That's how the negative exponent works, right? We put it on the denominator of a fraction. Yeah, that one gets written real cleanly. Now, if you try to do 1 divided by e, you're going to get a really weird decimal. But that looks nice and tidy that way. Oh, let's go backward now. If I give it to you exponentially, can you write it logarithmically? 10 to the fourth power equals 10,000. Well, it's going to be log base 10, but I'm not going to write log base 10. I'm just going to write log. The value is 10,000. The exponent is 4. Remember, the exponent is always the number that's off by itself when we put in logarithmic form. E raised to the pi power is approximately equal to 23.141. Okay, so it's log base e, but I'm not going to write log base e. I'm going to write ln, the natural logarithm. So ln of 23.141 is approximately equal to pi. If you want to have some fun with your calculator and try to raise e to the pi power, and yeah, you better get a decimal that's pretty close to 23. E to the 0 power equals 1. Of course, that makes sense, right? Any number raised to the power of 0 has to equal 1. So I've got a log base e, but of course I'm not going to write log base e. I'm going to write ln for natural log. The value is 1, so natural log of 1 equals, and of course the exponent is 0, so natural log of 1 equals 0. Now, if we were in the classroom at this juncture, I'd say, hey, we're going to do a little bit of practice with a worksheet. We're not in the classroom, but I'd still like to have you do a little practice with a worksheet. Worksheet should have been sent to you in an email. It's also available in the homework section of Quick Schools. Right? If you want to download it and type, and then save it as a Word document, or download it, type, and save it as a PDF. You can email it to me as an attachment. I'll get it. If you'd rather print it and work with a pencil and show your work in pencil, no problem. Just take a photograph of that, email the photograph as an attachment. Or if you're like, hey, I don't really want to use a lot of ink or toner, just get out a sheet of paper, copy down the questions by hand on paper, and then show your work that way. Right? Whatever works best, because I know if you do a lot of printing, you might not realize this, but mom and pop will quite often say, man, do you have any idea how much money you're running me in ink? And so if it's a case of, holy cow, we got to save a little bit of money, I'd be more than happy if you just do it handwritten on paper. Or if you want to download the document, type your answers, save it, email it to me. Again, you're not using printer ink at home, right? Whatever works best for you, I'll be thrilled and happy. The only thing I want to point out is if you do take a photograph of handwritten work, please make sure it is legible before you email it to me, right? If it's too dark, or just too small, or if it's not all in the photograph, doesn't do me a whole lot of good, right? I really want to be able to see what you've done. So the first section of today's worksheet is a matching. So there's 8 equations written exponentially, 8 equations written logarithmically, and they should match up 1 to 1. So for example, if I'm looking at question number 1, I'm like, hey, looks like the base is 3. I better make sure I can find an equation that's log base 3. I'm like, hey, the exponent is a 5. I better make sure that one of those says equals 5. And then, of course, there's a value of 243. So I'm like, okay, I better find one that says log base 3 of 243 equals 5. And if I can find one, I can then just take that letter and write that letter in the blank right before question number 1. While that first section might seem a little too easy or a little bit silly, this is where it's going to slow down a little bit. But again, these are very, very, very similar to those examples that I went through on the PowerPoint. So when you get to like question number 9, you say, hey, log base x of 81 equals 4. That's just gibberish. I don't understand that. Rewrite it, right? X to the 4th power equals 81. And you'll say, hey, here's an equation. I bet I can solve this equation. If you successfully complete the worksheet, we also have an IXL. The IXL is going to ask you to convert between exponential and logarithmic forms. And my hunch is that you should be pretty successful with that also. Again, any questions, if you need clarification on anything, please send me an email. I'm going to try and respond promptly to emails from about 9 in the morning till 2 in the afternoon. Now, I may end up taking a lunch break, or I might find myself getting dragged around the block by the dogs, or I might be making lunch for my kids. But except for a few minor times when I'm away, I'm going to try respond to any emails as quickly as I possibly can in a very timely manner. So if you've got questions, shoot me an email and I'll try to respond quickly. And if I notice that I'm getting questions, I'll probably be much more attentive at staying right by my computer thinking, okay, I'm going to answer this question, but I'm going to wait, because I bet if the student asks a question and I answer the question, they might have a follow-up question, or they might not have understood my answer, and I'll be expecting another email from you. So if I do get an email from you, I'll probably really, really monitor my email much more closely, and I'll try to get back to you as promptly and quickly as humanly possible. Best wishes, good luck. I wish we were doing this in person in the classroom. I miss seeing all of you. As a classroom teacher, the best part of being a classroom teacher is actually interacting with the students. And I miss interacting with you. And when all this is over, I'm looking forward to when we're all back at APL and we're all interacting again. Until then, take care and try to do the best you can with the math.